Yeah, yeah.
Everybody back. We'll hope so. Okay, we're going to talk about power and specifically DC power because it's different than AC power. Frequency and phase gets involved, so we're not ready to do that yet. It's defined as the rate at which energy is expended or absorbed. Now remember, energy is constant in the universe. So you don't create or destroy energy, you just transform it. You can convert it to heat, you can convert it to light, whatever, but the total amount of energy is still the same. So if you got a battery, has a charge on it that's got contains so much energy, and when you supply that to some kind of circuit, that energy gets transformed into heat or light, mechanical motion, or something, and it goes from the battery to those things, but it's still the same amount of energy in the universe exists. Just like charges, for every positive charge, there's a negative charge. So when an electron moves from an atom, the total number of charges are still the same. You've got the same number of protons and the same number of electrons that you had in the beginning. They're just separated. So you see dipoles, what they call those. James Watt, who's the steam engine guy, kind of did all the research on power, and we call watts, or a unit of power, after him, and we use the capital W because it's, again, a proper name, and it's equivalent to 1 joule per second. So that's the amount of energy per second, okay, that we're expending to do 1 watt. And if you remember, a joule was 1 watt second, or 1 coulomb volt. Okay, so we had a coulomb of charge at a 1 volt potential would be equivalent to 1 joule of energy. So the formula down there is all those things and how you get back to current times voltage. They represent 1 watt of power. So we have a nice little pie chart for this one. This one really spells pi. You do the same thing, P, I, and E. So P is equal to voltage times current, or in the order of the chart, current times voltage. It doesn't matter. You can transpose them. I've just worked through different versions of the formula, and at some point, if we substitute Ohm's law into the power formula, we can come up with power is equal to E squared over R if we have resistance. And we say we know voltage and resistance, we didn't know current, but we want to know what the power was. Or we have current and resistance, we don't know the voltage, but we want to know the power. So if you do that substitution of Ohm's law into the power formula, you can get these other variations of it. So we have a similar circuit with a resistor and a voltage source. In this case, it's the 13.8. I picked that because that's a typical nominal battery voltage, and it's what most amateur radio equipment uses as a voltage source. So that it can be portable and operated on a battery. So like if you buy a base station radio, typically you'll have to buy a power supply for it that supplies the 13.8 volts.
What's your average voltage for a ham radio?
As far as AC current or AC power?
I guess, right?
Well, the power, like I said, most of them will require a separate power supply to generate the DC 13.8 volts, and they will run off of your normal household power, 110 or 240, if you have that kind of service. If you're asking,
I guess what I'm asking is if you are, so if you're in a remote, if you're creating something where you would create your own voltage,
okay, you need
what would
13.8 volts DC.
that would be it?
Yes. Now you could get
Okay.
that from a solar array. You can set up solar arrays with a charger and it'll, generate 13.8 volts approximately. And you can run your radio off of it. Normally you would have a storage battery in the circuit because the solar voltage is going to vary. And when the cloud comes over, you don't get nearly as much. So you kind of need a storage battery there to mitigate it. And that's a typical setup for portable operation. People that go out and do parks on the air, summits, things like that. A lot of times we'll have a solar panel array that generates 100, 200 watts and a battery when the charging system's set up, and they can essentially operate all day as long as the sun's out, or just operate off a battery until it runs down. And, you can get all that stuff to fit in a backpack or what they call a go kit. Does that answer your question?
Yes. Yeah, I think so, pretty much.
Okay. Well, if it doesn't, ask another one.
So do you want to ask if the crank?
Oh, so the crank can obviously work, but could you also use one of those self-motion kind of contraptions where it's self-motionizing, kind of self-cranks itself?
That creates the
Like-
the current.
Yeah, basically unlimited energy within the doohickey thing.
Like those commercials you see with the little portable radio with a crank on it that charges up a internal battery.
Yeah,
I
basically,
know.
but you know those contraptions where scientists have made movement, momentum,
Like almost an infinite movement.
so that, like, you know, when you go to a museum and you go to one of these little areas and it shows and you spin them and it keeps moving by itself for like almost like for infinity, really.
I mean, like perpetual motion.
Yes.
Yes,
There you go.
that.
Well, there is no such thing as perpetual motion for real because there's losses.
Due to resistance and things like
Right.
that, correct?
Right. Mechanical resistance, air resistance,
Unless we
friction,
lived in a vacuum.
current resistance, which generates heat. So, your energy is getting transformed into other forms. But
I suppose the conversation that we're having, and not to get off topic, is if it's possible to capture as it's lost, you recapture it somehow. But anyway, that's a conversation for something else. But so what we're kind of getting at is there a way? We just basically wanted to know the basic voltage or power that is required if you didn't have a source of power that you could plug into, for example, and you created it yourself.
okay, well, most of amateur radio transceivers today, the modern ones, solid state, are going to require 13.8 volts and usually at least 20 amps of current.
20 amp of current.
Most of the transceivers will put out 100 watts. And they're probably 50% or 40% efficient. So
Efficient,
you
meaning
need
as in
100
how long it will
watts
last.
into it in order to generate 100 watts out.
Okay, thank you.
So if you had a solar array of 500 watts, you could, and a battery bank of 200 amp, batteries, 200 amp batteries, that would be perpetual enough to keep you rolling.
Yeah, you'd run all day.
Yeah.
Wouldn't be perpetual, but yeah.
I got a question real quick. I just want to confirm. So when it says I squared and E squared, what does that specifically mean? Because that didn't get into my brain.
It's the current squared
Mhm.
or the voltage squared, just the way it works out in the formula.
Okay. Okay. Cool. So basically, when it shows like a little spot where it says current, you're basically just times it to the to the second power.
Right.
Okay.
Yeah, that's what the two means, the second power.
Okay.
And I just worked 3 examples there with those 3 different variations of the power formula.
Mhm.
We're using 13.8 volts and the different current, and you can see they all came out to the same amount of power.
Mhm. Right, because it's a DC. Okay.
Okay, so how much power is delivered by a voltage of 13.8 volts DC and a current of 20 amperes? So if you got your little pie chart, okay, we need to solve for P, so it'd be I times E, or E times I, however you want to label it. So it'd be 20 amps times 13.8 volts, or 276 watts. You shouldn't need the calculator to do that. But, and in mention on the calculators, I would say in most exam sessions, they probably don't want to let you use your cell phone as a calculator because it would be too easy to cheat. How much power is delivered by a voltage of 12 volts DC and a current of 3 amps? So once again, it's current times voltage, or 36 watts. How much current is required to deliver 60 watts at a voltage of 12 volts? In this case, we're wanting how much current, because we know the power. So we divide the power by the voltage and get 5 amps. Which term describes the rate at which electrical energy is used?
Charlie.
Charlie. Defined as the time rate at which work is done or energy emitted or transferred. Electrical power is measured in which of the following units?
Bravo.
Bravo. Bravo.
Bravo. The rate of doing work in watts. Capital W. What is the formula to calculate power in a DC circuit? So if I want P,
Alpha.
so it's the EMF times the coulombs per second or joules per second. Oh, and back once again, you notice we have 2 answers down here in left field, so they can't be correct. How much power is delivered by a voltage of 13.8 volts DC and a current of 10 amperes? (138 watts). Oh, and you notice, everybody wasn't here when the question came up. These numbers or letters and numbers that you see represent the sub-element and the group and the question number that's in the pool. These are actual pool questions. And it says that for sub-element 5, group C, this is question number 10.
So the question will be the
Bravo.
same. The answer will be the same, but the distractor may not. So just because it's distractor, what? 12 volts, whichever distractor it is, it may be a different distractor on the test. So don't memorize distractors. Memorize the answer.
Because they're gonna be mixed, what you're saying is it might not always be in that order.
Might not-
Right.
Gotcha.
A may not be 4.8.
That's right.
Because one of the
So know
things,
the answer, not the
Yes.
order.
And then on these two pie charts, pi, the actual PIE would be, they're usually using times more than they are division, whereas the first one was more division than time.
I don't know.
It's the same, it seems like,
Yeah.
no difference.
I mean, yeah, it could be with the questions are more oriented that way. One of the reasons that you'll see the A, B, C, and D rearranged is because on the in-person test where you do it with a booklet and an answer sheet, the way we grade it is a plastic template with holes punched in it for the right positions. And they tend to manipulate the order of the answers. So the same answer sheet or template can be used multiple times for different exam booklets. Okay. Oh, no. I guess everybody got Bravo, right? How much current is required to deliver 120 watts at a voltage of 12 volts? So we want I, and we know E
Bravo.
and P.
Bravo.
Right? Okay, so that's the easy one, right? All you do is remember your pie chart and what a watt is, and you're golden. So that's 4 more questions you'll probably get right.